Hey guys, we're going to have a look at molecular shapes and polarity. It's part of the section of matter and materials, and getting a good understanding of this is a fantastic foundation to understand intermolecular forces, which is the video we're going to do after this. But just before we're getting into molecular shapes and polarity and so on, a great place to start is bonding. And just a recap of what types of bonding are there and how does the whole thing work anyway. So bonding is where we're going to kick off. You'll probably be quite familiar from last year and a revision this year that there's three types of bonding. Let's quickly run through them. Ionic is the first one. What happens in an ionic reaction or formation of an ionic bond? Well, in this case, it results in the formation of ions. Okay, so the word gives us a great clue as to what the basis of that bond is, which is basically a charged particle. So we're going to form charged particles. The only way things become charged is if they lose or gain charge. So we know that electrons are being transferred in this type of bond. Typically, it occurs between a metal and a non-metal. So that's the basis of it. We do have to look at the important factor of electronegativities, which I'm sure you're familiar with, just to actually see what the difference is and whether an ionic bond will occur. But it's when you've got extremes on the left, which is the metals, and the right, which is the non-metals, and you've got very low electronegativities here, very high electronegativities there, you're going to get an exchange of electrons or a transfer of electrons. Let's just have a look at a quick example. Sodium chloride, fantastic substance. You get sodium, which is basically an explosive metal, chuck it in water and boom, you're going to get a fantastic reaction. And then you get chlorine, which is a toxic gas they used in the First World War to asphyxiate the enemy. Real shocking stuff. And what happens when you put these two disastrous chemicals together is they form a match made in heaven, because the sodium is desperate to get rid of its one extra electron and the chlorine is desperate to receive it because it's got one extra gap. And so they form sodium positive because it's lost its electron, and chlorine with all its original electrons plus the newly inherited one from the sodium now has a complete outer orbital, so it's as happy as Larry, and it is negative. So the bond is actually just because the plus is attracted to the minus. So that's an ionic bond. Covalent bond, again, the name is really helpful. Co, company, corporation, communication, something to do with togetherness. And valent, like valence shell, the outer shells, bringing together the outer shells. So what happens to the electrons in this case? Well, they're bringing together, what's happening is they are sharing electrons in this case. So this is typically non-metals on the right-hand side. Both of them are wanting to gain electrons to fill up their outer orbitals. But so you can imagine these two oxygen molecules come to each other, and unlike the sodium and chlorine, which worked out a very amicable deal of giving and taking, the two oxygens, one is saying, hey, hang on a second, I need two more electrons. Have you got two electrons? And the other one says, no, I need two electrons. I need two electrons from you. No, you give me two electrons. No. And you get the big argument. And they say, no, okay, chill. I've got a plan. What about we share instead of trying to take from each other? So they work out a very friendly arrangement. And the one oxygen says, okay, well, I'll share two of mine if you share two of yours. And so a double bond was formed, and they lived happily ever after. Okay, so Cooper notation would look like that, Lewis diagrams look something like that. So this is a sharing, and typically it's non-metal to non-metal, so non-metals. Okay. This is particularly what we're going to look at when we're doing molecular shapes, because these don't form molecules as such. They form giant lattice structures, because the Na will then actually have a Cl on this side, and then the Cl will have an Na, and so on and so on and so on. So a repeating lattice when you get crystals of ionic compounds being formed. Just have a look at one more. Water is a classic example. Marvelous substance, water, where the H's have one to give, and the O is looking to gain two. So it hooks up with two H's, and then we've got a couple of things like that. So Cooper notation of water, very familiar, H2O, something like that. So that's covalent. The third type of bonding I'm not going to put up on the board because we hardly ever deal with it at a sort of a deeper level, but just for your information, it's metallic, which is obviously metal to metal, and what happens there with the electrons is a sea of free electrons forms. So you get the center of the atoms is all tightly bound, but the outside ones are kind of, well, they're delocalized. So they're not strongly bound to a particular nucleus, they just wash around. And it's almost, I mean, a loose picture is, you can imagine, bricks with concrete in the middle, cement holding it all together. That's kind of how a metallic bond works, in summary. Okay, so that's the essence of bonding. As I said, we're going to look particularly at the covalent ones when it comes to shapes and polarity. Okay, so shapes. There's 5 shapes that you need to know, most schools. Some of you have learned an extra 2, which I'm not going to cover. You can look at those in your textbook. And they're pretty straightforward. Have you ever been on a long car journey? Nice road trip, you know, from Joburg down to the south coast, or from Cape Town up to PE or something like that. When you're a little kid, they seem like forever, ever. And there's a little principle that takes place on the back seat of the car, which is very similar to what happens in a molecule. So, the way any of these shapes work is that you've got a central atom. Okay? So we'll look at the main atom in the center. In fact, I can use very colours that I have. So here's our central atom, and around the central atom, it's got this bond stuck. Around the central atom form the other atoms. There we go. All right. So when we just have one atom to add on, no, I can't get it to stick in. Here we go. So when you've got your central atom and only one other atom to add to that central one to form a molecule, then you could add it on wherever you want. There's absolutely no objection. This little kid has the whole back seat to himself. Okay? So he can sit wherever he wants on the back seat. So that's a very simple little arrangement, and we would call it a linear arrangement, simple linear arrangement. Add in a sibling and things become interesting, especially 7 hours into the trip, because suddenly it's, this is my side of the chair, no, this is my side, and there becomes a natural repulsion between the siblings, which forces the one to sit exactly opposite where the other one is going to be. They get as far away from each other as possible. And this is what we call the valence shell electron pair repulsion. Okay, valence shell is the outer shell. The electron pairs repel each other and get as far away from each other as they possibly can. Okay, so it's still linear, but in this case it's now symmetrical. If we add in a third sibling, a third bond to this little scenario here, what happens is these guys have to shuffle over a little bit. My molecule shape is nearly the right kind of concept, and we basically form something like that, all right, where we should have it at 120 degrees. The 360 gets split into 120, 120, 120, but it's still within a plane, and that's called trigonal planar or trigonal plane, depending how you want to pronounce it. Now the fourth one, 4 kids, okay. Now this is getting complicated. You have to buy a big SUV, excuse me. But assuming we don't have an SUV, we're going to have to fit 4 of them on the back seat. Hope the police don't stop us and check for safety belts and that kind of stuff. But what happens is we actually move into 3 dimensions. And if I stretch my analogy, maybe we're putting our kids in the boot. In fact, that's what I did when I was a kid. We used to sleep in the boot amongst the suitcases. I had a tough life when I was young. But what happens is that 4th one pushes the other ones down, and we end up with this shape. It's not quite how I envisaged. That's a bit better. There we go. The 4th one pushes the other ones down, and we end up with a tetrahedral shape. Okay, it's moved into 3D. Hard to draw on the board. But basically the angles have now moved from 120 and it's pushed down to about 109, something like that. Okay, now, importantly, so the first three shapes, linear, trigonal planar, and then tetrahedral. Now, I just want to grab something, excuse me. Okay, now, what we've been assuming thus far is that all the electrons in the valence shell are being used for bonding, all right? But that's not always the case, because sometimes there's an electron pair, like we saw with the water molecule, which is hanging out there, but it's not actually attaching another atom to the central molecule. That pair that's not bonding is called a lone pair, but it still has an effect on the shape. So you could consider two aspects to the shape. One is the electron pair geometry, which is like the stalks perhaps, okay? And then where there's a molecule actually attached, well, that is the molecular geometry. So let's assume that we take a molecule where there's only 3 bonded pairs and 1 lone pair. You can take this little atom off the end there. This electron pair still pushes the others down, so it looks kind of the same, except that this is what's making up the molecule, those bottom 4, the blue and the 3 red ones, okay? That is called a trigonal pyramidal, or trigonal pyramidal shape, because it's pushed into kind of a pyramid, okay? That's 1 lone pair. Take up another one, again, it's still tetrahedral in terms of its electrons, tetrahedral electron pair geometry, but the molecular geometry now is just looking bent, or angular, as we call it. Okay, and a great example of that is a water molecule. So that is shapes. We'll come to some examples that you can do just now. What I want to have a look at is polarity in the light of shapes. Let's have a look at water. Water, as we said, the hydrogen each share their electron with the oxygen. Oxygen shares back, and then there's the 2 lone pairs, giving it an angular shape. But what we're interested now is polarity. Now, polarity is all about electronegativities. The electronegativity is basically a little reading that you get off the periodic table, the little one on the right-hand side, that tells you how hungry that element is for electrons, how much it will draw the electrons towards itself in a bonding arrangement, and thereby making itself negative, electronegative. Okay, so looking at the values, oxygen has a value of 3.5. It's pretty hungry, number 2 on the charts. H is in the middle of the road, about 2.1. Okay, so when it comes down to the sharing of these two, it is not going to be even. Think of it like sharing pizza. If you and a friend went out for pizza, and how hungry are you? Okay, if you both, just come from school and you're pretty hungry, well, then you're going to share it evenly, 4 pieces, 4 pieces. But let's just say your friend kind of missed lunch, and you'd actually had quite a big lunch. Your mum had packed you sandwiches and chips and fruit and whatever other awesome things that you could eat. You might be generous enough to say, well, you're hungrier, you have 6 pieces, I just need 2. That's cool. And that's kind of what's going down here with the oxygen and the hydrogen. So they are still sharing this pair, all right? They are, in a sense, it's going around, that pair of electrons is orbiting both atoms, but it's spending more time at the oxygen because the oxygen wants it more. So because of its hunger, the electrons are there more often. Because they're there more often, it leads to a slight negative charge. And here less often, which leads to a slight positive charge. And of course, the same thing happens here. So that leads to a polarity in the bond. All right, so you see how polarity occurs in the bond? A quick run through the values that you need to be aware of in terms of the difference of electronegativity. Do have a look at your own notes and the way that your teachers taught it to you. But a way of looking at it is if there's no difference in polarity whatsoever, then it's a non-polar covalent bond, like oxygen bonded to itself, that one that we had a look at just now. They're both equally hungry, they have 4 pieces each, there's no polarity. Sometimes the cutoff point is 0.4. That's when bond starts to make, when the polarity difference starts to make a difference. But we can also consider it from 0.1 all the way up to about 2. or 1.9. Again, different textbooks, different teachers teach different things. You go with what you've been taught, okay? All of these do have a difference. Like here, the difference is actually 3.5 minus 2.1 is 1.4. So that falls quite high up the scale here to form a polar covalent bond. Whilst we're here, just there is a sort of a cutoff point of about 1. So anything up to 0.9 would be considered a weaker polarity, and anything beyond that would be a stronger polarity. And we'll get into that when we're dealing with intermolecular forces as to what's what. But let's just quickly have a look at what happens beyond there, from sort of 2 or 2.1 beyond. That is when your friend didn't only miss lunch, but they missed breakfast, and they didn't even have supper the night before because, I don't know, their house burned down. And so you, in your ultimate generosity, would say, yo, okay, listen, you just had this whole pizza. You look like you're about to fade away. And so it's no longer a sharing arrangement. You've actually transferred. You've actually given the thing. And that is where an ionic bond forms. Okay, so that's a little bit about polarity. And what you'll need to be able to do is be able to identify the shape of a particular molecule and work out whether it is polar or not. So let's have a look at one example just before we wrap it up. And that would be, say, ammonia. What about ammonia? So ammonia is NH3. Let's think through what the Lewis diagram would look like. Well, N is group 5, so it's going to have 5 electrons of its own. H is obviously group 1. So each H has got 1 to share. So I'll do it with slightly different colors so you can see it nice and clearly. There's the H's. And the N's will each share 1 with the hydrogen to satisfy those, but it still has 2 left over. So it's got 4 electron pairs, 3 bonded and 1 lone. So what shape is it going to be? Okay, it's got a lone pair and 4 others. So it's still based on the tetrahedral kind of shape, but it's got that one at the top that's pushing the others down. It's a trigonal pyramidal shape. Okay, so trigonal, trigonal, pyramidal shape. So that would be the shape. The question would be asking us, well, is it a polar molecule? Well, in order to work that out, you have to look at the polarity of the bonds. Well, N, what is the electronegativity of N? Electronegativity of N is 3,0. H is 2,1. So there is definitely a difference between them. There are polar bonds. So it's a trigonal pyramidal shape. It has polar bonds. Is the shape symmetrical or not? Well, no, it's kind of biased towards the bottom. So it's an asymmetrical shape, throwing things off balance and it's got these polar bonds. So therefore, the whole molecule would also be polar. If it's symmetrical, like carbon dioxide, where you've got the O on the one side and the O on the other side and the C in the middle, 180 degrees between them, they're kind of pulling against each other. So even though there's a bit of polarity in the bonds, the molecule is not polar because it cancels each other out in terms of its symmetrical shape. So if you've got an asymmetrical shape, which typically is when a lone pair is around, that's going to potentially cause polarity if there's polarity in the bonds. So check your shape, check the polarity of the bonds, and then that'll help you to work out whether the molecule is polar or not. Okay, do some practice with that, and we will get on with intermolecular forces just now. Ciao.